to start by talking about the particle in the gravitational field. And I'm going to start out with the complicated version, but I'm not going to go through it in detail. This is minus m integral d tau, and we can rewrite this as minus m integral, well, d tau is minus GIL dxi dxl to the 1/2. And that might look a little bit funny, but when you think about it, this is just dx squared. That's a square root, so what comes out is a dx, and it's effectively d tau. Okay, in the book, I work this out in enormous detail, and we get the equation that in fact, I'm going to write it slightly differently. du r d tau is minus gamma r il ui ul, or equivalently d2 xr d tau squared is minus gamma RIL dxi d tau dxl d tau. Okay, so this is the equation for a particle in the gravitational field, and it depends upon these connections, and we derive the connections as given by the inverse of the metric tensor multiplied by 3 different derivatives of the metric tensor. So everything's in terms of the metric tensor. Well, of course, as it must be, because the only thing in this equation is the position of the particle in the metric tensor, so there couldn't be anything. So that's why the gamma has to be there. I'm going to give a simpler derivation of this based on the equivalence principle momentarily, and after saying a couple of more things. Namely, what about the action of a particle in an electromagnetic field and a gravitational field? Well, then we would say it is minus m integral of minus GIL dxi dxl to the 1/2, plus, if it's charge q, integral ai of x dxi. Notice that what we want in every case is to have a scalar. So this is the mother of all scalars, but this is a covariant vector ai, a contravariant dxi, so this is also a scalar. And now if we go through if we vary the path by a path dx by a small amount, what we find is an equation, and instead of flipping the signs, I'm just going to write it as d2xr d tau squared plus gamma r il dxi d tau dxl d tau, and then minus q over m f. This is the Faraday tensor, in other words, E and B. Fri dxi d tau. So that's the equation for a particle, charge q, mass m, falling in a gravitational field where the x's are arbitrary coordinates, and then this is the expression where this is basically the curl of AI, the full curl of AI. Okay, now one more thing that wasn't in the book, but that I want to add to a second edition that I hope will eventually appear. Although I tell you, the problem with writing a book like this is that it's extremely broad, and then every individual subject is extremely deep. Because, you know, GR, there are all sorts of deep questions. Anyway, all right, so maybe we should turn just a bit to this board. So now, let's basically consider a different part of the action, and this is minus a quarter FKL plus the magnetic constant times AKJK, and all that square root of G T4x. G is the absolute value of the determinant of G nu, where Gij, lower index, covariant metric tensor. And now if we vary A, it'll be apart from here, and let me just go to the second equation. I think this is worth writing because it's simple enough that we won't be doing it all day. Partial XL FKL square root of G. You see, it's this square root of G plus mu 0 JK square root of G, and all this is variation of AK before X. So you can see that the field equation then is going to be, since this has to be 0, and the variation of AK is arbitrary, but we have it vanish at the endpoints because we want to. We then just get that inside the square brackets we have to have 0. So that's d by dxl square root of G, and let me divide by square root of G, FKL equals mu 0 JK. So I just divided through by 1 over square root of G, because otherwise the equation would have a square root of G here, which is fine. But the reason I divided through by square root of G is that this is the expression we derive for a covariant divergence of a contravariant vector. Remember, we went through that razzmatazz having to do with the with determinants and cofactors and so forth. It was enormous simplification, and that's where this comes from. But you see here, in a sense, this is a lesson really for all of us about physics, and it's that if you write down the action, if you get the correct field equation without knowing how to do the covariant divergence of a contravariant vector, you automatically get this equation just from the principle of least action. So, really, as far as I know, all of physics is wrapped up in the action being the scalar with maximum symmetry, and then you just vary things, and boom, all the equations pop out. And this is a lot simpler than having some approach through differential geometry with a Hodge star and all that. I do that in the book, but this is I think this is how God views it. Yeah. All right. Principle of equivalence. Okay, so let's, what is it, first of all? Well, the idea is that I'll explain it physically and mathematically. Physically, the idea is that if you transform, then you can always, if you have some particle in a gravitational field, you can make a change of coordinates such that in the local vicinity of the particle, And how small that has to be, I don't know. In many practical astrophysical applications, it's the size of the solar system is small enough. Otherwise, it might be the size of the Earth if you're doing particles falling around the sun. If you're dealing with particles falling around falling in a gravitational around the Earth, then maybe you need something the size of this room. Unless the particle is near the ground, in which case maybe you want something this big. In any event, you can change the coordinates where of a certain spatial dimension, a certain temporal dimension, such that within that, the metric of space-time becomes the ordinary metric of special relativity, and in these coordinates, the physics of special relativity applies. There's no gravity at all. So that's the picture. In other words, gravity is due to the coordinates that one uses, which, well, this was all local, of course. And an example of this, my favorite example, which I experienced many times when I was on sabbatical in China, I was at Fudan University, and at Fudan they have a building with two huge towers that are 30 stories high. And I was on the 26th floor. And so to go for lunch, I go into the elevator, press ground floor. Of course, this is China, so normally the elevator is packed. In any event, the elevator, if it was lunchtime though, everybody was going to the ground floor. And so zoom, the thing would accelerate going down, and I'd feel very light. And then the elevator would stop accelerating, would come to its constant speed of descent, in which case I would feel heavier. And I always thought that we were going to stop at another floor, but no, we were just on a constant velocity, and if I was lucky, we were going to go all the way down to the ground floor. Okay, so that's an example. If, in fact, the cord in the elevator had broken, then we all would have been in free fall, and we wouldn't have felt any pressure on our feet, and we would have thought, well, there's no gravity at all, until of course the damn car hit the bottom of the shaft, in which case we would be disappointed. Anyway, so that's an example. Now, a way of thinking about it mathematically is that when you make a change of coordinates, well, what are we talking about? We're talking about eta ik, where this is the flat space Minkowski metric of special relativity. The change of coordinates, if we go back to those coordinates, then it's partial xj, partial yi's. I'm taking y to be the coordinates. Well, which are y now? Now I'm confused. Arbitrary coordinates. These are the free fall coordinates. Thank you. G, JL, partial XL, partial YK. Okay, so these are the, yeah, this is obviously right. So these are the equations that transform from the arbitrary, from the actual metric, or the metric of space-time in the x-coordinates to the metric of space-time eta in the y-coordinates. But we can always do this at one point, but we can't do it in general everywhere, because this GJL in general is reflecting curved space, and so you can't make curved space flat in more than one point at a time, or one tiny region at a time. Okay, so, but suppose we look at these equations. Well, what is the equation of motion in the y-coordinates? Well, the equation of motion in the y-coordinates would, of course, be this equation. But in the y coordinates, gamma is related to eta. Eta has no derivatives. Oh, that's another thing. When I said that we had to make the thing particularly small, I want to make it so small that there are no first derivatives of the metric tensor. So not only is the metric tensor eta, but the first derivatives of the metric tensor are 0. Then gamma is 0 there. Okay. So that's why it's a little more than just simply. You see, this is an orthogonal transformation, so you can always obviously choose coordinates such that this is non-zero. This is eta. You go from G to eta. But what we want is we also want that that this is true enough in a small region that the gammas also vanish. Okay, so what is the equation then in this region? The equation in this region is d2yi d tau squared equals 0. In other words, the particle falls in as though it had no gravitational field at all. And d tau squared is minus eta I k dyi dyk. Okay, so now let's look at this equation. Let's transform back now to the x coordinates. And so what is that equation? Well, it's d by d tau of dyi d tau, but dyi d tau is dyi dxk d tau. And this then is dyi dxk d2xk d tau squared plus partial 2 yi partial xk partial xl dxk d tau. I'm running out of space here. dxl d tau. So all I did here was use the chain rule. In other words, d tau applied to that, d tau applied to this gives the second derivative. d tau applied to this first derivative gives the second derivative times another derivative. So it's just a chain rule. Now we multiply both sides of this equation by partial xm partial yi, and that's to cancel this term, to make this a delta km. And when we do that, we get this equation, d2xm d tau squared plus gamma m kl dxk d tau dxl d tau equals, well, 0. Okay. So what we've derived then is the geodesic equation from the equivalence principle. This equation, of course, is the same as the one over there. It's just that I flipped the gamma to the other side. And so that's quite important. And the affine connection here is gamma m kl. And if we want to be pure, we put this gamma m kl like that to distinguish the upper index from the others, just in case we lower the m. But actually, I mean, it could be, you see, that this thing was the L index raised to become an M and the M lowered. So this is a technically more correct way of doing it, but I don't think anyone was puzzled. So this is partial xm, partial yi, partial 2yi, partial xk, partial xl. So that's what the gamma is, because you see we multiplied both sides by partial xm, partial yi, and that hit this thing. Here it gave us a delta function, a delta, Kronecker delta, but over here it gives us a complete expression for the, let us say, it's the affine connection is what people call it. And we see here that it's given by derivatives of the coordinate transformation from the inertial coordinate system, which is the yi's, to an arbitrary other coordinate system, the x's. All right, now, we're going to make a break now to other topics. So if somebody has a question or a real need for a fruit snack.
I'm good.
All right. Okay, so the next topic then is to look at this equation, or equivalently that equation, which is the same thing really, for the case of slow motion in weak gravitational fields, so that we make some contact with Newton's theory of gravity, and maybe look at simple corrections to Newton's theory. Okay. So the first thing is that we have here ui is dxi dtau, but u0 is dx0 dtau, and that's c dt dtau. So this dt dtau is more or less 1. But c is a big number compared to slow speeds. On the other hand, dxi dtau is a v. So ui compared to u0 is what we call beta in special relativity. In other words, v over c. So we're going to ignore this relative to that as a first step to do slow speeds. We're thinking of a plane landing on an airfield, and we better have this small compared to that, or the passengers are in deep trouble. All right, so let's go back to this blackboard then and see what our equation becomes. It's 0 is dur dtau plus gamma r 0 u0 squared. Remember, the u's are just dx mu dtau is u mu, or dxi dtau is ui. So we've gone to that point, and this guy is essentially c squared. And so we only need gamma r 0. Well, we have a formula for all the gammas. And gamma r 0 is a half grk. And now we have g0k comma 0 plus g0k comma 0. Well, that's funny. One of them should be k0, I think. Minus g00 comma k. Okay. But we're talking about weak static gravitational fields. Okay. So if the gravitational field is static, we can forget about these two terms. And so this is just minus a half grk g00 comma k. Okay. And moreover, G00 is 0 because that would involve a time derivative. I see David is rifling through the book in search of something, so that might be time to ask a question.
Do you have a typo on 11.2.2?
Say it again, what?
I wonder if I just saw a typo.
Where?
Maybe not. 11.264.
Let me look at where this is. Where?
Should one of those be an M or not?
No, I think that's correct,
Okay.
because we're doing the divergence.
Great. Thank you.
But you get a candy anyway.
Okay. Thank you. Oh, I see. Yeah.
Okay, so let's continue with this case. So what does our equation look like? It's D2x, whoops. By the way, I heard a story from Mark Price. He said he was taking general relativity, I think at MIT, from Weinberg. And at one point, Weinberg was talking about something to the class, explaining something, and meanwhile writing a very complicated equation on the board. The equation had nothing to do with what he was talking about. And Price said, how is it that he could write something correctly and talk at the same time? Well, that's because he was Weinberg. All right, anyway, D2 XR d tau squared then is, all right, first I skipped something here. What are we going to say about this? Well, we're going to say that Gij is eta ij, the metric of special relativity, plus hij, where hij is very small. And so this equation here is going to be gamma r 0, 0 is going to be equal to minus a half this is just going to be the r derivative, effectively. And so this is just h0, 0, comma r. So it's the r derivative of the 0, 0 component there. And so the inverse metric tensor would be the thing that makes this 0. So we have Gij would be, I think it would just be eta ij minus, well, no, it'd be just plus that because we just raise everything. All right, anyway, to get back to this then, this dxr d tau squared is then, because of the minus sign there that comes up here, this is equal to a half u0 squared h0, 0, comma r. But now u0 squared is essentially just c squared. And so the equation then, and in fact we're really talking about the space derivatives here because the time thing is just going to be 0. Because the h0, 0, comma 0 is 0 because everything's static. And so what we have then is d2 x3 vector dt squared, we're basically setting t equal to tau, is equal to c squared over 2 grad h0, 0. And now, if phi is Newton's potential, so it's phi is Newton's then what we want is G00 is -1 plus H00. And we're going to set that to be -1 minus 2 phi over c squared. So H00 is minus 2 phi over c squared. So finally, what do we have when we stick things in there? What we have is d2x dt squared is equal to minus grad phi, which is, if we're talking about a particle falling outside a large mass at a distance r, then H00 is 2 gm over r c squared, and this then is equal to grad of gm over r, or minus gm r vector, well, I should call it x vector, over the length of x cubed, where here r is length of x. So it is a bit of two different notations for the same thing. All right, so what we've done here is we had to have r essentially the same as eta, which would be a -1 for the 0, 0 component. And then we picked this so that we get the familiar equation. That's how we figured out what the scale factor was. And I hope I didn't screw up a minus sign. So you might ask, well, how big are these gravitational fields? Notice phi over c squared is dimensionless. So this H00, if we're talking in terms of Newton, it's Newton's potential over c squared, which is interesting because I'd hadn't often thought of Newton's potential as having the dimensions of the square of a speed, squared velocity. All right, anyway, how big is that? Well, phi over c squared is of the order of 10 to the minus 39 on the surface of a proton. So you're really close, but on the other hand, there's not much there. 10 to the minus 9 on Earth. 10 to the minus 6 on the Sun. I think that's the symbol for the Sun, but it may not be. And 10 to the minus 4 on the surface of a white dwarf. So what that means then is in almost every case, these approximations that I've been making are excellent for the static case. And of course, in most cases, these things are static. All right, the next topic is time dilation. And have you all seen the movie Interstellar?
No.
You still haven't seen it?
No.
You should see it.
Okay.
The reason is that if you see the movie Interstellar, which is quite a good movie, probably the best science fiction movie ever made. If you see the movie, you'll always get the sign right for gravitational time dilation.
Okay.
And well, I don't want to spoil the movie.
I think somebody has spoiled it for me.
Huh?
Somebody spoiled it for me already.
Oh.
So, yeah.
Well,
don't worry about it.
one of the characters spends a day, I think, on a planet that's very near a black hole. And when he finally gets back to Earth, everybody that he knows is very old. And that's because there's the time dilation factor meant that one day on this planet was like 70 years on Earth, and so his daughter turns out to be an old lady when he gets back.
Yeah, I knew that.
Okay. Anyway, it's Kip Thorne advised the director on how to do most of the stuff, and the director accepted most of Kip Thorne's advice. There was one part of it, though, where the director refused, and it was actually an interesting part. It's where the spaceship goes in free fall through a wormhole.
Okay.
Or something, I assume. Anyway. Now, if it's in free fall, then, there's nothing calmer than free fall. Nothing should happen. But the director didn't want the major part of the voyage to be quiet and peaceful. So he has the spaceship rattling like crazy, whereas actually it would have been totally silent.
Yeah.
Like an elevator when the cable snaps. It's great to get to the ground. All right, so let's do gravitational time dilation, and let's just look at detour. Well, it's 1 over c, because because this thing is ds squared. And so this is minus gij dxi dxj, or equivalently, it's minus g00 dt. So in other words, c detour is dx0. This is kind of dx0, So this is basically so in other words, what we've got here is, in one set of coordinates, the dx spatial are 0, and we only have a dt. And in the other coordinates, we have all these things happening. Okay, and so what's going on here? Well, in here, what we've got is minus g00 is 1 plus 2 phi over c squared, or 1 minus 2 gm over c squared r. That's just the same thing that we use over here, putting the two together, basically. So what we're talking about is that g00 is just slightly what? Minus g00 is a little bit less than 1. And so, in other words, we have dTau is equal to square root of minus g00 dt, or 1 minus 2 gm over r, over c squared r dt. Okay, so these are our laboratory coordinates, and this is the actual proper time. And so what you see here is that dTau is less than dt. And so in other words, dTau is the proper time for the guy on that planet, and it's much less than the laboratory time here. And this was first verified in an experiment. Somebody said it was a clock tower. It wasn't a clock tower. It was explained to us correctly by Z, and then incorrectly by a subsequent colloquium speaker. But do we get the whole thing here? Okay. And at Harvard, there was a tall tower erected so that a certain physicist would come from, I think, Johns Hopkins to Harvard. This was back in, I don't know, the early part of the 20th century. We're going to be going another 15 minutes, actually, because we started late.
All right. That's all good.
So, I mean, if you want, just come in and sit down. Don't stand out there. It's too tiring. The tower was never used for very much, but until Pound and Rebka used the Mossbauer effect to measure the change in frequency of photons that went down the tower. The tower is maybe what we would say 5 stories high, something like that. And if you apply this formula to this case of 2 clocks in a high tower, what you find is that T lower over T upper is approximately 1 plus the local acceleration of gravity, this is our favorite 32 feet per second, times h over c squared. And that's what they actually verified. What they did was they were doing frequency measurements, and nu lower over nu upper was 1 plus gh over c squared. And so the lower clock was slower because it was in a bigger gravitational field. As I said to the students before you came in, if you want to understand some of gravitational time dilation, or at least get the sign right and the magnitude right, watch the movie Interstellar. And the change here, the lower frequency minus the upper frequency over the average frequency was gh over c squared, which in the case of Pound and Rebka was 2.46 times 10 to the minus 15. And that was so small a number that they had to use the Mossbauer effect. With modern technology, people at NIST with atomic clocks can observe this time dilation very simply. They just have the atomic clock run at, they have it on an optical table with some sort of a jack underneath it so they can raise and lower the table, and they can see the change of the rate of time of the clock as they raise the thing 2 feet, say, in the Earth's gravitational field. This was something that was actually illustrated here by one of our, I think, former graduate students who's now at NIST, and he gave a colloquium here a couple of years ago. I actually had dinner with Thorne last summer, and I told him about this. He hadn't seen the demo that the NIST people did. All right, I think we finished up with that part of the board. And so you might say, well, what's the redshift of the sun? Because after all, if the photon comes off the surface of the sun, it has to climb up in that gravitational field. And what is the redshift in the energy and the frequency? And the answer is using essentially the same formulas, that nu is equal to nu zero times the square root of minus g00, and this is the nu zero square root. It's basically the same formula, 1 minus 2mg over c squared r, but now for the surface of the sun. And this is a shift of 2 parts per million. So delta nu is 2 parts per million in frequency. And that's, I imagine, something that's very easy to measure. Well, even with ordinary methods, let alone this stuff. Okay, well, the next topic is just to define the curvature tensor. And this is RI, MNK. So this is a monster tensor. It has 3 lower indices and 1 upper index. And it's defined in terms of the derivatives of the affine connection gamma. And so this is gamma Mn comma K minus gamma I Mk comma N plus gamma I Mk comma, let me get this right. In fact, yeah, I got it wrong already. It's gamma I Kj gamma J Nm minus gamma I N J gamma J Km. Now we can write this somewhat more nicely by thinking of it as Rnk, thinking of this as a matrix, and this being the Im entry of this 4x4 matrix. In that case, we can write it as the commutator of essentially 2 covariant derivatives. So this is kind of a Yang-Mills way of writing it.
Okay.
That commutator and then the Im matrix element, where these gammas are 4x4 matrices. And just to write this out a little bit more explicitly, it's gamma N comma K minus gamma K comma N plus, and let me change the notation slightly, gamma K commutator gamma N. These are 4x4 matrices. This is just the commutator. And now we take the Im element of that matrix. And what are the gammas? The gammas, well, gamma K, I'm not going to write the whole thing out, it's in the book, but let me just show you what it is. It's gamma K, it's actually this way, gamma K0 over here, gamma 0, K3, down here it will be gamma 3, K0, and then over here it's going to be gamma 3, K3, where the K is this K. Okay, so that's writing it in terms in matrix form, and this looks very much like the Faraday tensor, the Yang-Mills generalization of the Faraday tensor.
Okay.
So it's a commutator of 2 covariant derivatives in the Yang-Mills sense. Okay, another definition is the Ricci tensor. This is RMK, which is a contraction of this Riemann 4 tensor, and it's N, M, N, K. And then the scalar, the curvature scalar R, is then a further contraction. It's GMK RMK. So this just gets us to the scalar, the Riemann scalar. All right, well, the next thing in the book is an application of all these ideas to something really simple and familiar, namely a 2-sphere in 3 space. No time, you could have time, but I don't take explicit I don't actually talk about time explicitly there. On the other hand, my feeling is that we ought to just skip this section. It's really very clear in the book, I think. But unless you want me to do it, in which case I can do it in class. We've got about 4 minutes left, I'm estimating.
Skip?
Does anybody have a question?
No, I think we skip it.
Did you say skip? Okay. All right, if we skip that, which I encourage you to read, and send me email with typos, let's go to Einstein's equations. And once again, the easy way to derive them is from the action principle. But before we get there, we have to say something about what causes gravity, and what causes gravity is energy and momentum. And this takes us to a perfect fluid of pressure P, density rho, fall velocity ui, and the energy momentum the stress energy tensor Pij is then, for this perfect fluid, is P Gij plus P plus rho Ui Uj, where Ui is the fall velocity of the fluid at any particular point. Okay, and the idea that the reason for going to this is that general relativity is hard enough as it is, and so what we don't want to do is put over here something really complicated. So this is the simplest way. What I'm aiming at here is cosmology, and so we imagine that we have basically a universe that's homogeneous and isotropic, and consequently the P's and the rho's are basically not going to change, not really for practical purposes going to be functions of anything but time. They're going to be the same everywhere and so forth. Anyway, there's a special important case here where P and rho cancel. You might say, how could that be? But it can be. I'll talk about this later. This can happen when the energy is potential energy. And when the energy is potential energy, and if the potential energy is the same everywhere, then if you increase the volume of your box, the energy goes up. Whereas if you have conventionally, we have a gas in the box, and we increase the volume of the box, the pressure drops, the temperature drops, and so the energy in the box, in fact, the way in which if you expand the box, what happens is you just let the pressure of the molecules inside expand the box. And then their energy goes down because of the work they do expanding the box. We have a medical leave there. And so that's when you have positive pressure. You expand the volume and the energy goes down. If you have potential energy everywhere, expand the box, you get more energy. And so pressure is negative. I think we can stop at this point, especially since David is gone. Do you have a question? All right.